This is not a very quantitative talk. This is just to throw some ideas at you about some of the things we could be doing for SETI, because I think that maybe we should consider some other ideas. We do consider other ideas, but this is mostly to provoke you. And so let's do that. To begin with, of course, the idea that we're alone, it's unproven whether we're alone or not alone, of course. But on the other hand, if you think that this is the only world where intelligence is defined by you being able to build a radio transmitter so you can judge for yourself whether you're intelligent or not. If you think this is the only place where that's arisen, and there are plenty of people who believe that, then you believe in miracles, right? Because after all, this is the order of magnitude of the number of planets in our galaxy. If you talk to Jeff Marcy and ask him what fraction of the stars have planets, he'll say, well, probably a half. Or maybe more, and a half, of course, is the same as 1 for astronomers. So, that's a large number. We don't know how many of those are, of course, habitable worlds. Kepler will answer that in about another 700 days. One of the most interesting experiments, certainly of this century, and maybe of several other centuries. The smart money, which is to say the people who work at NASA Ames, figured that they'll find a few percent of star systems have Earth-like worlds. If that's the case, then the number of Earth-like worlds is on the order of tens of billions in our galaxy. Right? So that's a big number, and it's hard to believe that they're all sterile or they're all merely infested with single-celled life forms. Okay, now let's get on to SETI. This is a fellow who's somewhere in the audience shaking his head, no, no, no. That's what he promised to do all during this talk. There's the antenna Frank used 50 years ago to look at 2 nearby sun-like stars about a dozen light years away, and he established the strategy for targeted searches, which are the kinds of SETI experiments we have traditionally done here at this institute, not exclusively, but that's the sort of experiment we do mostly, where we take the telescopes and we point at certain spots on the sky. We don't survey the entire sky in general. The people at Berkeley do that, but we don't, on the assumption that if you're looking for life in the desert, maybe you should skip the sand and just look at the oases. So we tend to look at star systems individually, and Frank had done that. He'd looked at 2 stars. He was optimistic enough to think that looking at 2 was a sufficient sample that maybe success would occur. We now know that it's not. And we've looked at more stars, but not an enormously larger number. In fact, the number of star systems that have been looked at carefully over a wide range of frequencies with high sensitivity was done with the SETI Institute's Project Phoenix, which extended over most of a decade, used antennas in Australia, Greenbank, West Virginia. Clearly the aliens are arriving. And in Arecibo. Okay, but that number is fewer than 1,000. Fewer than 1,000, and I hardly need to point out to you that 1,000, a sample of 1,000, is also not very large. Okay. In fact, this is a graphic, and Joe probably knows the history of this graphic. This is a graphic that was made for a popular, I think it was an article in Scientific American. Yeah, Scientific American. Anyhow, and so it's some years old, but it isn't substantively changed from what you see here, showing the amount of search space, how much of the parameter space has been looked at for SETI signals. And of course, the parameter space shown here is only a small fraction of the actual parameter space. There are only 3 shown here. In fact, of course, there's something like 9 parameters you can think of easily, polarization, sensitivity, and so forth and so on, that are not here. Well, actually, sensitivity sort of is. But in any case, this is very sparsely populated. That's the point, right? And so when you hear people commenting on the fact that, well, SETI's had 50 years to succeed and hasn't, that doesn't mean anything. Right? You can say it does mean something. Paul Davies has said that in his latest book, but even he will admit that it really doesn't because the sample size is still too small. All right. Now, the Allen Telescope Array, which I think many of you have already heard much about the Allen Telescope Array. I know Joe has given talks about it and others here, is designed to remedy a lot of this problem by increasing the amount of search space we look at. And indeed, this is an old graph now that I made numerous years ago when our hopes for funding were somewhat more sanguine than they've turned out to be, but in any case, so this assumed that the Allen Telescope Array would be up to a couple of hundred elements by now. but you could just shift this curve to the right depending on your views of future funding. And what it shows is how far out into the galaxy this kind of instrument can do targeted searches, right, at reasonable sensitivity and over a wide range of frequencies. And so obviously it just goes out for a while until you get to the point where you're so far out that the galaxy now begins to look flat, and then it changes shape a little bit and then continues to go up. The interesting thing in this graph, of course, are those numbers at the bottom. These are the ends in Frank's equation, the Drake equation, and they show when you can expect success if you think this experiment could find a transmitting society. Carl Sagan figured there were 1 million societies in the galaxy broadcasting, and if that's the case, then success is not far off. If you take Frank's number, which is the most conservative of the generally proposed numbers, 10,000, then it takes another 24 years for success. But there is something to be garnered from this. You could say, well, I mean, this all assumes some value for n. Yes, it does, right? It also assumes that this instrument is capable of finding the signals, which, yes, it does. But on the other hand, these are the premises of the whole SETI enterprise, ever since the beginning, right? These were the bases on which the first experiments were done and subsequent experiments were done. So you can believe them or not, but if you think that SETI has value, that the premises are reasonable, then what this says is that success is not 3 generations down the road. It will happen within a generation, or there's something wrong with the fundamental assumptions. Okay, now, there is another point here that it's kind of a leitmotif for this talk. So I hate to dignify it with that term, but yeah. And that is that we have assumed in our targeted searches that the aliens are patient, that they have perseverance, right? Now, what do I mean by that? That means that they are targeting, at least maybe not us, but this direction for long periods of time. Okay. Now, here you see a number. This is the typical sensitivity of SETI searches. Some are a little better, a lot of them not quite as good, but that's a typical number, 10 to the minus 25 watts per meter squared. By the way, that's obviously not many. That's not many ergs. It's been said that all the energy collected by all radio telescopes since the first experiment is the amount of energy expended by a flea hopping. But nonetheless, that's the number. But here's how you can translate that number. If the aliens are 1,000 light years away and they have an antenna as big as the one down in Puerto Rico, then we would hear them, even at 1,000 light years, which is quite far. They're 1 million stars more within that distance. If their transmitter power is 6 megawatts, we would hear that. Okay. Now 6 megawatts is not so much. I mean, the Arecibo antenna has a radar set. It has a Klystron on it, which is running, I think, at 2 megawatts now. Certainly 1 megawatt. So, essentially, with the kind of equipment we can build, we could hear these guys at certainly hundreds of light years away and maybe 1,000 light years away. But the assumption is that they're always on the air. That when we look, and we typically look at a given star system at a given frequency for only a few minutes, 2 minutes, 3 minutes, 4 minutes, that they're sending a signal our way. Now, this has been likened to the possibility that, you fire a pistol and your bullet happens to intercept a bullet coming the other way. I'll get back to that. There is this question, however, will the aliens really do this? Would they relentlessly target the Earth? Okay. That quickly leads to discussions, particularly if you put this on the web or someplace like that. This leads to discussions about alien sociology, which, as Chris Chival pointed out to me once, has a very sparse data set. And in particular, what would motivate them to relentlessly target us? One suggestion is that they are aware of our manifold difficulties. People somehow think we have more difficulties now than we did, for example, in the time of the Romans. I would submit to you, they probably had more difficulties then. But anyhow, well, they're worried about what we're doing to the environment, or they're worried about what we're doing to endangered species, or they're worried about what we're doing to, the institution of marriage, or whatever your favorite thing is. So they want to get in touch to help us. So that gives some motivation for them to relentlessly aim their transmitters our way. Well, let me just point out to you that that's not going to work. We've been broadcasting our presence for, the first FM radio broadcast was 1938, I believe, at least in the United States, and I think that was the first anywhere commercial. But say since the war, we've had high-frequency, high-power broadcasts, FM, television, radar. So 60, 70 light years out, you could find Homo sapiens. Beyond that, I don't know when you could find Homo sapiens. It'd be very, very difficult. I mean, how could you find the classical Greeks? How could you find even the Victorians? They didn't have electric lights till the 1870s, almost 1880s, right? So it's very, very difficult to find us until after the Second World War. Now, within 60 light years, right, the number of stars is on the order of 8,000 or 10,000, but in fact, they can't be more than 30 light years away at that distance in order to have had enough time to pick up I Love Lucy, decide they don't like Fred Mertz's jokes, and then send relentlessly this transmission back to us. But a couple of thousand stars is not a big number. In fact, I submit to you that that is too few, that is too small a number for anyone to know that Homo sapiens exists. This may help you to sleep better at night, knowing that nobody knows we're here. It should also give pause to the people who claim that we're being visited, which is about 1/3 of the population. Because there is you laugh, but you know, 1/3 of the people in here. I get emails every day from people having difficulties with aliens in their personal lives. But, you know, you do have to ask, why are they here now? Why did they come and abduct the trilobites? And you could argue, well, maybe they did, and the trilobites didn't write it down. That's true. But it is remarkable that it should be happening just in time to improve your social life. Okay. So I think this has a consequence for SETI. See, they don't know we're here. So they can't be targeting Earth because they're trying to get in touch with our species. They don't know about our species. Well, the obvious rejoinder to that is to say, well, that's okay, because they're just broadcasting to the entire galaxy. But that turns out to be expensive, at least if they do so at a level that makes it easy for the kinds of SETI experiments we've run to detect. They would need, for an omnidirectional broadcast, on the order of 10 to the 17 watts with the transmitter power. Now, you know, they can save a few factors or two here and there by confining it to the galactic plane and so forth, but you don't save orders of magnitude by doing that. So 10 to the 17 watts is a lot. That's kind of Earth's insulation. That's the total sunlight falling on the Earth. And as Barney Oliver used to say, you know, waveguides melt. He would say that, I mean, he would say that in context that really didn't have anything to do with any of this, but it's just a good comment. But what he was trying to say is that very big transmitters, you know, there may be limitations to very big transmitters. Now, Jim Benford's in the audience somewhere, and he's done a lot of thinking about how you can build very big transmitters and beacons and so forth. But if you're going to go to an omnidirectional broadcast, this is the power requirement for you in order to make something that would be easily detectable by us. So summarizing this little argument here, the idea of looking for always-on signals, I think, founders on the fact that there's no obvious motivation for them to target Earth in particular, and to target everywhere is very expensive. Okay? So that doesn't sound to me like there's this always-on powerful signal. How do we deal with this? Well, we can be smarter. One way to be smarter, of course, is to forego the assumption that they're broadcasting at such a level that our experiments could have detected them. And that's not so crazy. I mean, this is our sensitivity, but that's only 100 years after Marconi, right? And of course, the extraterrestrials don't know when we invented radio, and they may have assumed we invented radio 100,000 years ago, and that we have instruments that are far more sensitive than this. And indeed, one sort of proposal that's been made by Frank Drake, Claudia Marconi, and Eshelman at Stanford, a very good idea is that what you really want to do is, send spacecraft out about 550 AU or a little beyond, and use the sun as a gravitational lens and make that your antenna. At which point you get on the order of 10 to the 7th to 10 to the 11th gain over whatever antenna you put out there. And that's the way to do these searches because, with that kind of amplification, I mean, in the optical, that kind of amplification would allow you to see our street lights. The sum of the street lights from cities at the distances of the stars quite easily. So maybe that's what they're assuming, that they assume we know that they have that capability, right? Or that we have that capability, I guess is what I'm really trying to say. Because that's not so far into the future. I mean, you can't do this today. You can't send, a radio telescope out 550 AU, but you certainly could within a century. Right? So maybe they're assuming that we're at least a couple of centuries further along than we are, and consequently they have very much weaker transmitters than the kinds of things we could have found. Right? It's very much like looking for hydrogen in elliptical galaxies. We couldn't find it for years and years and years, but when you have adequate sensitivity, it turned out it was pretty easy. Okay, So maybe we could do at least some experiments where we had, much lower threshold for signals. That's a very obvious brute force approach to improving SETI. One possibility, the square kilometer array, which is, a decade or two or so down the road, that'll have 10 times the collecting area of Arecibo, so that gives you 3 times farther into space at any given level, but maybe a factor of 10 in signal sensitivity. And maybe they'll build it in a 2-dimensional way, which will, of course, scale better than 3-dimensional antennas. I mean, even if you took a 100-meter antenna and you just sort of beat out all the low-frequency anomalies in the receiver so that you could really integrate for a year, you could get a sensitivity of maybe 10 to the minus 29th watts per meter square per hertz. And that's maybe 2 or 3 orders of magnitude better than anything that's been done. So that could find beacons that are weaker, 10 to the 13 watts. 10 to the 13 watts, by the way, is, you add up all the power plants in the world, and that's 10 to the 13 watts. That's kind of expensive, but maybe not inconceivable. So that's just sort of a brute force approach. Another way to be smarter about SETI would be to consider special cases. Now, this is an approach that's got a long history. This is one of the earlier ideas, and I remind you of it. This is a supernova opportunity. Guillermo Lemarchand and others have pointed out this idea. A supernova goes off somewhere in our galaxy, maybe somebody else's galaxy. So all the astronomers, these are the Klingons here. Right? So all the astronomers on the Klingon world have got their antennas, their telescopes aimed at this supernova because, of course, there's something to be learned there. But one of them is clever enough to say, wait a minute, just wait half a Klingon day, whatever that is, 15 hours, and then let's aim a transmitter the other direction, 180 degrees away. Right? So Earth is down here somewhere, and at some point we see the supernova, so all the astronomers are looking at that supernova, and then half a Klingon day later, we get this message from the Klingons saying, hi, we're the Klingons, you want to join our book club. So, this tells you, see, the advantage of this scheme is that it tells you where to look and when. This is an idea that I floated at a meeting years ago on the island of Capri to, I should say, modest reaction, so I'll try it again here. That is, binary stars with planets. This is not impossible. You can have binary stars with planets. You can either have very close binaries in stable planetary orbits that are, maybe 5 times the separation around them, or you can have a situation like this where the stars are separated by, say, at least the distance between the Sun and Saturn, and then you can have stable planetary orbits, around each of the stars. Suppose you had a system like that, and, intelligent life arose on one of the planets around one of the stars. It would very quickly take advantage of the planets, if there were any, or even just orbiting devices, around the other star. They're in a double star system. They're going to take advantage of that situation, and there'll be communication back and forth. The interesting cases are the ones where the stars are aligned in such a way that they eclipse one another, so-called eclipsing binaries, as you see in this little animation, because now, if you look at these cases, when they eclipse, when they get in front of one another, you're looking right down the communication pipeline between the 2 star systems, and you could expect signals. Okay, so the suggestion here was, why don't we look at such double star systems? The problem with this idea is that we don't really know about many double star systems that are separated by the distance between the Sun and Saturn. The reason is that they have periods that are measured in tens of years, and so nobody knows about them. But there's the idea. Okay, again, it tells you where to look and when. Another obvious thing to do is look in the infrared. We do optical SETI experiments. This is Shelley Wright up at the Lick Observatory. This is an experiment that Frank was actually running for a while. This box here was built mostly by Dan Wertheimer at UC Berkeley. It has several photomultiplier tubes in it. I think it has 3. It uses this 1-meter telescope to look for nanosecond flashes of light coming from nearby stars. There are several experiments to do this at Harvard, at Berkeley. It's a good thing to do, but it's all being done in the visible for obvious reasons. We're at the bottom of an atmosphere. There was a proposal in the NSF to remove the atmosphere so we could do this in the infrared. That was not funded. So, but you could do this. I mean, obviously you could do it from space. And there was some talk from some guys in the Netherlands, actually, who were proposing experiments to put on an infrared telescope in space, that they have a SETI component. But I don't know what happened. I don't think anything happened. But clearly, if you have infrared telescopes, you can beat this rat. The dust in the galaxy really limits your visibility to stars that are maybe less than 1,000 light years. Okay. So if there are really, there are long distance transmissions in the optical, you really ought to go to the infrared. Another possibility, look for a really intermittent but very, very big signal. Right? Now when I say a very big signal, I mean, it was a suggestion of Jack Welch at some meeting. It was an offhand comment he made during one of his talks in Paris sometime before the invention of the compass. And what Jack said was that, really, there ought to be transmitters out there that are so powerful, optical transmitters, that even cows could see the signal. Right? I gave a talk once about cow SETI. I thought this was a clever idea. You can work the numbers. How big a laser does it take to ping the Earth with a bright flash that even a cow could see, even if they don't write it up? Okay? And it turns out that's a big number. But you could still expect something that's maybe as bright as a fifth magnitude star, something that somebody could see with their eye. Because if there was a flash of light in the sky tonight, right, and that was seen by a lot of people, you would study the heck out of that part of the sky. It only needs to be a 1-bit transmission telling you there's something in that direction. And then you would expend a lot of resources studying that direction, presumably looking for the far weaker signal that would tell you that there's something interesting there. Now, one way to look at these big honking signals is an idea that Frank had broached during a coffee break once. And he pointed out that the moon is actually kind of a garden ball reflector, right? And so at radio frequencies. And so if you just look at the moon, you're essentially looking at the entire universe, or at least half of it, actually more. Okay, you're looking at the whole universe like looking into a garden ball. You see the whole sky at once. Right? So if you're looking for meteors, for example, maybe that's a better way to do it. Right? The problem here is that because of the geometric effects, your sensitivity is down by 50,000 or thereabouts. But if you're talking about a really, really powerful signal, maybe this is worth doing. Maybe somebody should just be aiming an antenna with a 30-minute beam at the moon all the time, looking for something. You need 2 of them, because if you just found one flash, maybe you wouldn't know what it was. If you saw 2, you might think it's a lunar phenomenon. Who knows? But this is not such a crazy idea. All sky all the time. Here's another, what I think is an important point for SETI being smarter, and that is the fact that, in a way, we have been broadcasting longer than since the Second World War. They know about our chlorophyll, right? Because that's a 2 billion-year-old signal. They know that there's oxygen in the atmosphere. And that might serve as an incentive for them to do something about us. Now that depends on how many worlds show chlorophyll. Let's assume that life is commonplace. Maybe 1 in 100, 1 in 1,000 planets develop oxygen in their atmosphere. I mean, of course we don't know. But if that is a common enough occurrence, then maybe advanced societies who've got the funding to build the kind of instruments that could find these, build the terrestrial planet finders and so forth, they may have long lists of so-called bioworlds. And we're just on that list because they found this planet at some point. They found that the Earth has chlorophyll. So here you go, Zork. Here's another planet with life. Okay. Now, if there's large numbers of these, then it's maybe not so unreasonable to assume that some of them may have developed intelligent life. Okay. So maybe they go through the list. Right? They don't spend a lot of time on each one because, we've had chlorophyll for at least a couple 100,000 times longer than we've had radio transmitters. But if you have a list of a few 100,000 of these, then it's not unreasonable to assume that one of them might get your ping. So here's a straw man idea. Maybe they do an optical ping, 1 billion targets, if they have that many. All you need is that 1 bit. Just tell them, we're here. This is this part of the sky you need to be interested in. So if you give them a nanosecond that can ping, you can work out, all right, a sufficiently bright flash that it's easy to see with almost any experiment. That's a duty cycle. Well, all right, so that's a 5 gigawatt laser. That's not impossible. It's not impossible. And this could be an automatic experiment that all it does is just goes and pings, 100 million or 1 billion known worlds with life, telling them this is where to look. And then you have some sort of omnidirectional antenna that's obviously a far lower power that has the information, whatever that information is. Encyclopedia Galactica, whatever, used car listings, whatever it is that you want to broadcast to the galaxies. So I think that considerations like this lead me to think that a 2-tier transmitting strategy from the aliens' point of view actually makes sense. The first tier is just to get somebody's attention. Just the 1-bit signal. Just the 1-bit signal that's very intermittent. Okay, so ping these bioworlds, for example, with these very short, here I am signals. By the way, if you make the signals sufficiently short, that also reduces guessing at the other end about what frequency to look at, because it's at all frequencies. And the message, of course, the actual bits, the information, that's in the harder to find signal, but that's the signal that you would continue to look for as long as you could. By the way, this is also interesting because when you shorten a signal by a factor of 2, right? But for the same energy expenditure, now the amplitude is twice what it was. The noise has only gone up by the square root of 2. So it's actually more, it's more efficient to have short signals rather than longer ones. Okay, so just to summarize that logic again. They don't know we're here. So we're in a, Earth is not special particularly. We're just in a list of worlds known to have biology. If that list is not long, it's not, it's not so good. But let's assume that it is long, greater than 100,000 or something, because the time scale for life's existence is far longer, we think, than the time scale for intelligent life existence. Maybe we'll prove that wrong. That would surprise me, but it could happen. Okay, so that means that they'll be sending pings to lots of worlds. The ping will be intermittent. It will be short. And maybe we should have some more experiments where we look for very short pulses with reasonable rep rates. We don't know what the rep rates might be, of course, but minutes to days. That's just a guess. The group at Berkeley actually does something like this. They have something called astropulse, and they're looking for microsecond pulses, not short ones in this. And the message is that always on weak isotropic signal. Okay, let me just give you a concrete example of another way to beat this synchronicity problem, this intersecting bullets problem. This was a short experiment we did here at the SETI Institute this last summer. I already said that. And that is to use as a clock transits of the sun. Okay. So here you see a planet transiting the sun over and over. It doesn't seem to bother going around the back. We thought, here's a clock that tells the aliens when and where to broadcast in our direction. Send a signal that arrives when we are transiting the sun as seen from their world. Okay? So all that means is that all we have to do is look in this direction opposite to the sun all the time. And we will eventually get this ping from somebody who's noticed our transit, knows that this is an Earth-like world. Well, obviously it is an Earth-like world. And they send a signal to arrive here during that transit as seen from their star system. So we will see it in the anti-sun direction. We proposed this this was a poster paper at a bioastronomy meeting back in 2004. Together with Ray Villard and I did it. And we thought, all right, this is a clever idea. But then it turned out, after we wrote it all up, that yeah, maybe it was a clever idea, but we weren't the first to think of it. Actually, guys across the street at NASA Ames had already written something about it in 2000. Well, those guys are smarter than we are. But it turned out that actually, and I thank Peter Backus for pointing out the fact that the Russians had actually thought of this in 1988. As far as I can tell, all the ideas in SETI were thought of by the Russians in the 1970s and 80s. The Russians are always claiming that they invented all this stuff first, and I now believe it's probably true. They probably did invent everything first. Anyhow, so the idea isn't old, but it's not a bad one. It's actually, I think, a pretty good one, because again, it tells you where to look and when. And so we did this little experiment here, just using Allen telescope arrays, so here are the people involved. And this was presented at the International Astronautics Congress in Prague a couple of weeks ago. It's just a preliminary experiment. But what makes it interesting is, A, the fact that it does tell you where to look, but also the fact that it makes it a little bit easier on the aliens. They don't need 10 to the 17 watts to make this work, because they know exactly where you're going to be. You're going to be transiting that star over there, okay? And even if they have a transmitter that is kind of sloppy, and they just, send a beam that fills the entire solar system out to, say, Jupiter, thinking you're probably not farther away from your sun than that, then they only need a 2-watt transmitter. It's like a flashlight, okay? If they're better than that, if they can make the beam smaller to the size of the sun, because they know you're transiting the sun, so you're in the beam. If they make the beam the size of the sun, like that, then of course they only need 2 microwatts, right? It's less than a laser pointer. And if they can find the Earth in front of the sun, then they only need a fraction of a nanowatt. So this makes it cheap in terms of the energy consumption, right? It's a completely different order of magnitude in terms of the power requirements. However, there is this. tells you where to look. There is this. If they're going to do it just as you're transiting the sun, they need to know the distance from their transmitter to the sun to within a few light hours. Right? That's pretty good astrometry. Maybe not impossible. That's parallax measurement good to 10 to the minus 8 arc seconds, which is 500,000 times better than Hipparcos. Well, that's better than we're doing, but on the other hand, it's only 150 years after the first parallax experiment succeeded here on Earth, so maybe they can do that. But actually, it's not really necessary. Right? As long as they send a ping every 5 hours or something like that, it really doesn't matter because it will eventually intersect you when you are transiting the star. And then at that point, they don't need any astrometry. Right? They just need to know. If they have a very narrow beam, then they need to know the proper motion of your star so that by the time the signal gets to you, you have moved out of the way, that kind of thing. But that's not so hard. Those constraints are not so bad. So in fact, this is not a very hard thing for them to do. And I think that, again, that this is something that we ought to try doing. We did try these preliminary observations in June and July. This was the configuration. 25 of the 42 antennas at the Allen Telescope Array were used. Those are the ones that were operating. We had a fairly large synthesized beam. We actually didn't want a synthesized beam, but that's the way the experiment was run. This is just a pattern of some of these spots on the sky that we look at. The system is not terribly well set up for looking at the sun, which is a moving target. So we need some good software development to do this again. But as I say, this was a preliminary experiment. We looked at a couple hundred positions, very tiny fraction of the ecliptic strip, in fact, and obviously for only 100 seconds at a time in any given direction. So it's very, very incomplete. But I do point out that this experiment could have found a transmitter, even if it beamed everything inside of Jupiter's orbit, it was only 15 watts or more. So, an interesting thing to do. And I think that we could do this experiment better because this seems like such an obvious thing to do, such a clever idea that makes such evident sense in minimizing the amount of cost at the other end, that maybe it's worth doing this again. More AAC antennas would allow you to do this much faster. The other possibility is to use a dedicated antenna, like this one on the just south of Groningen in the Netherlands. This is the De Wingelo 25-meter telescope, which at 21 centimeters has a beam which is, the size of the sun, half a degree. Right, so just perfect. And this antenna was actually mothballed a couple of years ago. This thing was built in the early 1950s. But they didn't actually they did mothball it, but there's an amateur group that has taken it over and shot it full of grease and made it work again. Okay? And I've been in touch with the guys there, and they say, well, you might be able to convince these guys, if you paid them a little bit of money, so those of you who brought your checkbook, pay them a little bit of money, we could put, maybe one of these astropulse receivers on this thing, and just have it spend a good part of the year just looking at the anti-solar direction. It's an obvious way to do it. Another possibility, it turns out that the Westerbork synthesis telescope, for those of you who know that instrument, you also a photo of it, is putting multi-beam receivers on the antennas, but two of the antennas will not get those multi-beam receivers, so there'll be two antennas sort of left over. And again, those are 25-meter antennas, same as this really. So those are things that could be used for this experiment. If you could get one of them to, just make it a dedicated instrument for looking at the anti-solar direction. Online, cheap pings, and it tells you where to look. All right, just finally, I do this in every talk, but I do want to point out to you that I always worry that we're being a little bit provincial in SETI about our assumptions about what's at the other end. These are the kinds of things that astrobiologists talk about in terms of what ET might be like. These are all essentially descriptions of your next-door neighbors. This is Hans Moravec's prediction of what your next-door neighbor will be like in 20 years. He's plotted here the amount of compute power you buy per dollar over time. And although this is a 10-year-old plot, the point is today for $1,000 you buy the compute power of a lizard. And by 2020, and which may be of interest to you if you're selling car insurance, and then the point is that by 2020, $1,000 buys you the compute power of you. And so the point here is that maybe this is the generation, or maybe it's the next generation, that invents our successors. Right? So if you ask what ET is going to be like, you can say, well, maybe they're going to be these guys that are sort of carbon-based, monochirality and all that stuff. But on the other hand, if they're only a couple of hundred years beyond the invention of radio, they may not be biological at all. Now, this has become a fairly commonplace refrain these days. A lot of people have been saying this now. I made this little graph a couple years ago just to show you what I mean by this. Here's the evolution of a horse, which 60 million years ago was the size of a collie dog, and not terribly useful for carrying chariots around or warfare or anything like that, but there wasn't a whole lot of that. 60 million years. So this is what Darwin did in 60 million years. Horses went from here to the size of a horse. This is what computers have done in the last 35 years. Right? I had a computer in 1977, had a 1 megahertz clock rate and 8-bit bus and so forth. The computer I have at home is many thousands of times better than that. So that's factors of thousands in 35 years. So that's the point, that this is all very much faster. Whoops. Now people say, yeah, but we're going to put the computers in our brains, so we'll go to some sort of board-like mentality. That may be, but this can never compete with the pure machines in the end. So I think you can forget these guys, these soft, squishy aliens. Ray Kurzweil was at the Institute about, 6 months ago, and he said, yes, this is inevitable. We're going to invent our successor. There's going to be machine intelligence, and they're going to be nanobots, and they're going to spread out. It sounds like the Three Stooges. They're going to spread out and start eating up the cosmos. Now, as far as we know, this hasn't happened, but of course, maybe we don't know. Maybe they've eaten everything except our local neighborhood. It doesn't strike me, and I asked Ray about this, but he was very evasive in his response. This doesn't seem to me like the way to go. You don't want to distribute, distributed computing is maybe not the way to go if what you really want to do is be a master of the universe, not to work on Wall Street, but to work in interstellar space, because you don't want time of flight problems between the various components of your brain. And what you really want to do is, another idea of Kurzweil's, use computronium, the maximum, highest density computing device, whatever it is. Here's a picture of it. It's strangely like your brain. Okay, so I think that probably they would be, compact. But really, the point is not so much how they're built, but where would they be, and what does this mean for SETI if this is true? If you only have a couple of hundred years of biological intelligence between the invention of radio and the invention of machines that pick up and leave and do their own thing, then where should you be looking for the majority of the intelligence in the cosmos, which is probably not biological? And that's a very difficult question, because you really have very little insight into what's of interest to these guys. I think you have some insight into what the first generation of these guys might be like. The AI people say, the first generation will instill moral behavior, which is to say, they'll behave well, they won't try and do anything nasty, so we won't have to pull the plug. But I think that the second generation is beyond your control. About the only thing I can think of is that, there are a few things I can think of, but they want matter and energy, so let's just stick with that. And so you might want to look at places where there's a lot of energy, which are places that, in general, we never look at with SETI, like O-stars, right? O-stars, big bright stars. A lot of the stars you see with your naked eye are these kinds of stars, big giants that are very, very hot. Lots of energy, but not terribly interesting for biological intelligence because they burn out quickly. So here you go, tens of thousands of times more energy than the sun. Molecular clouds, there's a lot of material there, and hot stars. We never look at molecular clouds. All right, there's the Orion cloud. So these, highly condensed clouds of material, very hot stars embedded in these. There's the Penrose idea where you throw your garbage at a black hole that you're circling, and you can extract a lot of energy that way. You can get a lot of energy out of a black hole. Whatever shortcomings black holes may have for your lifestyle, one thing they do supply is a lot of energy. So that might be a place where we should look. And in fact, I'll go further than that. There's a lot of literature on black holes as possible abode of intelligence. I kind of like Bach ovules because they nimbly fit just within the beam of our radio telescopes. And again, you've got a lot of material here, and usually some hot stars, is Bach 68. A couple of hundred solar masses of material, very cold. If you're a machine, maybe you want it to be very cold in your environment because that improves your thermodynamic efficiency. This is the only unambiguous singular point in the galaxy, the galactic center. The Benfords have made a strong point that this is someplace we ought to be looking. Again, Jill mentioned our experiment to do this actually at Westerbork for 4 hours, which was the amount of time that the Dutch Foundation gave us to observe. And they candidly admitted, well, we're going to give you this 4 hours of time, not because we think you'll have any chance of finding ET, but you may find some instrumental problems with the Westerbork telescope. It's hard to look at the galactic center because there's a lot of natural radiation that tends to mess up your receiver baselines and things like that. But this is a place where you really would want to look. Just the bottom line of all this is that the public, in particular, regards SETI as a static enterprise, right? That we're sitting around with the earphones, as Jodie Foster did, listening for ET, and that this year's experiment is like last year's experiment, except there have been a couple of 100,000 cups of coffee that have gone by or something. In fact, it's changing. This is just a plot of some of the biggest telescopes, radio telescopes, as a function of time. And if you threw out a few points, maybe this wouldn't be so obvious. But if you believe this point up here, and certainly you have to believe that point down there, there's a one or two orders of magnitude increase in size of the largest antennas per century. So that's one point. The instruments are getting better. Despite the vagaries of funding for any particular instrument, the instruments are getting bigger. And in addition, the speed of the search, and my index of the speed of the search here is the number of simultaneous channels that you can monitor. Those are the black dots here, and those follow Moore's law because that's just digital electronics. So you put all this together, and on average, SETI experiments increase in speed they double every couple of years. Okay, so it isn't the same experiment year after year after year. Having said that, this is a photo made at the basement of the SETI Institute, and it digs back on Landings Drive in June of 1997. And those of you who are familiar with some of the people that have worked here will recognize Kent Cullors in the front there, the blind physicist that was the prototype for the character in the Jodie Foster film, our CEO Tom Pearson in the back, and some other people who worked here. We had found a signal that for most of the day looked very enticing. And while this was in fact not ET, it was the SOHO satellite, it was a very, in my mind, very fortuitous thing that this little misidentification, which lasted, as I say, about 16 hours, occurred, because it showed what really happens if you pick up a signal. And beyond that, it was very exciting for a while. This hasn't happened for real, but what I'm trying to tell you is that if this enterprise is well motivated, it will be happening for real within your lifetime. Okay, that's it.
All right. I suspect there might be one or two questions for Seth. Who wants to start? All right. Thank you, Seth. That was great.
How many light years away could they detect our transit?
How far away could you detect our transit? The only limitation there is the brightness of our star, right? Because all you're doing is counting photons. So if you have a bigger, there's no real limitation because you can always go to a bigger mirror, collect more photons. Right? Then our planet dims the sun by about 1 part in 10 to the 4, right? So you can do the statistics yourself and work out how many photons. I mean, somebody here from Kepler probably could tell you how far away you could do that with a 100-inch telescope. My guess is on the order of 50, 100 light years, 200 light years, something like that. But is somebody here from Kepler who can?
Several people.
Yeah, here.
So the stars in the Kepler field of view, which are dim enough that they're not saturated and bright enough that they're distinct as stars to the instrument, are between 600 and 3,000 light years in distance. And there actually does get to be a problem when you're so far away that you're down to, that the sun looks like 18th, 19th, 20th magnitude, because that's at that level you have a background where every pixel has a star like that on it.
Yeah. So at that point, your confusion limit, right? Right. Okay. So it was probably that. Yeah.
Yeah, so one thing you haven't talked about is, without talking about monoliths on the moon, as it were, is what if they've actually put the probes, say, in the solar system? Are there potential techniques to find it that way? I mean, I appreciate it's a hard way to look, but you made the assumption they're always at their home star system, rather than they've already moved out the solar probes looking at us and maybe beaming information back in their direction.
Yeah, well, it's certainly been discussed, the idea of solar system probes. I always sort of wonder what's the point having a probe, because for them to report back takes as long as for them to wait for I Love Lucy. But on the other hand, the probe could in fact generate higher quality information. So maybe no aspersions to be cast on Desi Lu Productions here, but so there's a possibility. The difficulty is, as you've already noted, there are several difficulties. John Dreher used to always talk about the fact that small probes then there's, there are physical limits on antenna size. You need a big antenna. So there's a problem there. He felt there was a problem. But I think the real difficulty is where do you look and how? How do you find these things? It might be very cryptic, very hard to find. I mean, it's hard to find an asteroid that's the size of this building, right? So it would be difficult. Some searches have been made at Lagrange points 4 and 5. An optical search was made numerous years ago. You can find it in the literature. And they ruled out anything smaller than on the order of, between 100 meters and a kilometer or something like that, depending on the albedo. Okay. Frank has mentioned to me that they, in unpublished work, they actually aimed the Arecibo radar at one of the Lagrange points. But the trouble is the Lagrange points are very big compared to the Arecibo beam, so they didn't do those things. Frank, what was the deal there?
You just described, we did radar studies at but Arecibo can detect an object a meter in diameter or less, actually, at that distance. But the problem is that the Arecibo radar, because of computer limitations, can only examine a small fraction of the ray path in distance. And also the beam is small, and actually the things at the Lagrange points aren't at the Lagrange points, they wander around. So in fact, to study the Lagrange points, you have to study a large volume, and the Arecibo radar just doesn't do that. There's a narrow beam, and can only look over a small range of distances. And so, indeed, we searched, we saw nothing, but that doesn't say much.
I mean, I think it's a good experiment to do that, at least. If you're going to search the entire ecliptic, maybe the best thing to do is to look for NEOs, and maybe in the course of that search you find something.
Seth, there's a question.
I want to ask you, please, to explore the assumption that we're on a list of places with chlorophyll, and we have been for long enough that anybody who would be making such a list would already have been able to send probes and learn more about us and then maybe stop by. Is there any reason, that a species, after they've colonized a few planets, would want to do anything else than just silently buzz a place, especially a place that's constantly broadcasting things like widespread panic would ensue if there's ever any aliens detected. So, and just occasionally disable a few nukes here and there. After you colonize 5 or 7 worlds, what else is there to do? We wipe oil off birds, right? But we don't try to talk to the birds, at least not every day. I do occasionally.
Have you ever talk back? Some of them do, actually, don't they? Well, I don't know what to say to that. Unfortunately, I think that falls into the category, again, of alien sociology. And since, you don't even know whether the aliens are biological or not, in my opinion, most of them are not even biological. I think that they're going to be inscrutable, mostly. I don't know that you can second-guess their motivations. That's all I'm saying. And I wouldn't base too much of your search strategy on their motivations. Obviously, there's implicit in all of this is the assumption that they make some sort of signal that you can detect. That's a very fundamental implicit assumption. And that not even be justified. Sometimes some of my colleagues talk about the altruism, right? That they're willing to make some noise to let us know that they're there. Well, all you have to do is look at the controversy surrounding the matter of active SETI. It was just a little thing held by the Royal Society, in fact, in the UK a couple of weeks ago, in which we discussed whether we should be broadcasting. And Jim can tell you that it's a very, very heated debate whether even we should broadcast. This, despite the fact, I will stand on my soapbox for 3 seconds here, that we have been broadcasting for 60 or 70 years, signals that are very easy for them to find if they, for example, do something like use their own star as a gravitational lens. But this is very heated, so to say that what the aliens are going to do, I don't know that there's very good reason to believe anything about that.
Question here. When will we have our own list of bioworlds? How many worlds? How far out? And to what detail? And what sort of instrumentation will be required?
Well, I think that depends on your bank account. And the terrestrial planet finder, is now on sort of indefinite hold. It's really been sort of canceled. And that would have been the first step in that direction. Did you want to say something about this, Rob? Yeah. Yeah, it is strictly a money issue. The technical, I had a dinner with a colleague from Holland who works at Space Telescope Science Institute, Ron Allen, a couple of weeks ago, and he economy that all the technical difficulties, the technical hurdles for building such an instrument that could actually see extrasolar planets and get enough spectral information to look for things like methane and oxygen and so forth. These have been solved, but the problem is that there's not the budget. It's a budget problem. So this is one of those things that the answer depends on the money. I have so many questions to go, unfortunately.
Yeah, Seth, there actually was an optical search of the Lagrange points a decade or more ago.
Well, I referred to that one. That was the one that...
Yeah. And they didn't find anything larger than a Mount Flood.
Shine. Could have been dark.
Larger than, I'm sorry, Jim, I didn't hear that. Larger than a Volkswagen. Yeah, I don't think it was that small, actually, but it did depend on the albedo.
Okay, one last question in the back.
That's the back.
It's kind of a budget and technology question. So lots of charities are doing things like donate your car to our charity. And I'm wondering if the SETI Institute has considered, because there are zillions of satellites and companies are putting them out and they get decommissioned eventually, donate your about to be decommissioned satellite to SETI. We'll turn it around 180 degrees and we'll use it until it crashes into the atmosphere.
When you say satellite, you don't mean satellite dish or so many people. You mean...
I mean like orbiting the Earth, like communication satellites that
What would you use it for?
I don't know, could you use it to listen?
Usually they have pretty small antennas on there and not particularly good receivers.
They're mostly in the atmosphere.
Yeah, well, that's true. I don't know
Actually-
that many of them are very sensitive. And normally, if you put people say all the time, why don't you move this whole experiment into space? There's some places to move it into space that makes sense. Well, money, of course, but the backside of the moon is good because the backside of the moon is permanently shielded from all the noise here. But just putting it up into orbit, low Earth orbit or even higher, exposes it to like the RFI, the interference from a third of the Earth or more. Right? So that's not necessarily a very good idea. And these satellites, of course, are small. They don't have 100-meter dishes affixed to them.
And we now require that at the end of their lifetime they be boosted up so that they're not causing more debris.
But that's an insurance problem.
All right, can we thank Seth one more time?